One thing that we should think about is if we have a collection of vectors that's linearly independent, how could we add vectors to it, add vectors to that collection, and still have a linearly independent set? So suppose we have k vectors that are linearly independent. All of these are in some ambient Euclidean space, so Rn for some n. And suppose we want to add one more vector, and let's assume that that vector is not already in the span of the original vectors v1 through vk. So the question here is the resulting collection of v1 up through vk together with this one extra vector, is this linearly independent? Well, let's check. Suppose not. Then there is some linear dependence relation between them. So we'd have a1 v1 plus dot 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 plus a k vk plus some term with v in it. So, let's call it little a times v equal to 0. And this is with not all of the a's equal to 0, right? Because if these vectors are linearly dependent, then there's a non-trivial linear combination equal to 0. So that means one of these a's isn't 0. And there are sort of two cases. The first case is if little a itself actually is 0. In that case, this linear dependence relationship becomes just a1 v1 plus dot 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 up to a k vk equals 0. Right? The v term drops out because we're assuming for the moment that, or we're considering the situation where a is 0, so the v term drops out. And in this situation, since a was 0, right, one of these things has to be non-zero, but a itself, we're assuming, was 0. So that means that some remaining a, so one of the ai, is not 0. But that contradicts the linear independence of the original collection, v1 through vk. Right? We know we were assuming v1 through vk are linearly independent, and that means that a non-trivial dependence relation can't exist. So it actually can't be the case that little a is 0. So this actually isn't a possibility. So it must be that little a is 0. Or I'm sorry, little a isn't 0. Okay, but if little a isn't 0, then we can take our linear dependence relationship, right, a1 v1 up through a k vk plus little a v, and we can rearrange this. We can solve this equation for v, and when we do this solving for v, we have to divide by a, and that's why we need to know that a isn't 0. But when we do that, we get v equals, let's see, minus a1 over a times v1, and then minus a2 over a times v2, and so on, all the way up to minus ak over a vk. But if you look at this, this means that v is in the span of v1 through vk. But we said at the very beginning that v was some vector that isn't in this span. So we assumed that adding this extra vector made this collection linearly dependent, but we derived a contradiction, right? We contradicted the fact that v is not in the span of v1 through vk. So that means the assumption we made is actually false. So the collection v1 through vk and also v, we assumed it was linearly dependent, we derived a contradiction. That means that this collection must actually be linearly independent. This is a really common way to start with some collection of vectors that you know is linearly independent, and then make it a little bit bigger. As long as you can always make it a little bit bigger by adding a vector that isn't already in the span of these vectors. Then it's guaranteed to maintain linear independence.